So we have one final section. Now the good thing about this section is it's actually, well, this particular section on partial differentiation is revision. And I'm just going to do it because I'm going to do a section on error analysis that you actually would have done last year in semester 3, as it were. But I'm going to take the focus away from errors when you're kind of doing measurements to rounding error, which is something which I think is important and something for you to consider. Okay, so this revision section, I'm going to go, well, let's see how we get on. So you think of functions, so whether you have some idea of what a function is or not at this stage, well, hopefully we'll give you an idea here. In engineering anyway, you can think of them as a relationship between variables. Variables are just things you measure. So relationships between physical quantities. And with a function, it'll be one physical quantity given in terms of other physical quantities. So, for example, the force of gravity between two objects is a force of the masses of the two objects and the distance between them. And when you know those masses and that distance, there's only one force that you can have as such. Okay, so let's see examples. So area of a square depends on side length. And then we kind of have this notation, functional notation. So this kind of says that area is a function of side length. So when you know the side length, you know the area. And this is like f of x. So the area for the input s is s squared. Similar story, the height of a projectile depends on how much time has elapsed. So height is a function of time. Yearly sales of a product, temperature of a component depending on for how long it's been used. For beams of constant Young's modulus and second moment of area, we have that the load per unit length, W, shearing force, bending moment, slope and deflection all depend on the distance from one end of the beam. So this is something you've seen before. When you know the distance along the beam, you can calculate all those variables. The volume of a sphere. So consider for a moment the bending moment on a light beam of span 6 meters subject to a constant UDL load. So we see for each value of x, there's only one value of m. So for example here, and the points on the graph are of the form input, output, well, input, output, the input being the x variable, and the output being the bending moment at that point. Okay, so m equal to m of x is a function of a single variable, the distance along the beam. You just need to know the value of x, the distance along the beam, and you know the value of the bending moment at that point. Now, many functions in engineering, physics, and mathematics tie together more than two variables. So, for example, the force between two objects depends on more than one number, whereas this m of x just depends on one number. For example, the bending moment on a square plate, I think it's probably, I'm not sure, is it under a constant? It's probably under a constant load. Yeah, under a constant load. I think maybe it isn't. There it is, I think. So here the bending moment. So this, if you can imagine that, just as this kind of represents all the distances along the beam, this two-dimensional square here, actually I could take it down here if I wanted. This represents all the points on the square plate. This is a 6 meter by 6 meter plate. Okay, and one thing I'm not plotting the, so remember we normally plot the bending moment upside down. It actually, like here this is negative, but actually they're positive. I haven't done that here, or maybe I have. It doesn't really matter. You can think of the top or the bottom as being the square plate. And what we have is the bending moment depends on two numbers. You need two numbers to specify a point on the plate. So for example, maybe this point here is the point x equal to 4, y equal to 5. And we go up to here, and this you need 3 coordinates to specify a point on this graph. So if x equal to 4, y equal to f, and then the bending moment at that point is the so-called z coordinate. Okay. Another example, the second moment of area of a rectangle of height h and base b about the x-axis is given by this. So second moment of area of a rectangle depends on the base and the height. And one of the things you might be interested in is how does the second moment of area change when you change the length of the base or the length of the height, this kind of thing. So here we see how the second moment of area varies as we change h and b is easy to see from the above. So it says when the base doubles, the second moment of area doubles as well. And when the height doubles, the second moment of area not triples, is multiplied by 8. But what we want to do is use the tools of calculus. That just means your differentiation and integration to help us investigate functions further. Okay, so some examples of the kind of things: area of a rectangle. If you think of the material of the beam and the cross section being variable, you have that the slope, or say the deflection, depends on 3 things, and it could possibly also depend on a load parameter. So maybe for a constant load. So these are your kind of formulas: M max equal to WL squared over 2. Now here X doesn't play a role, but W and L do. So this kind of scenario, the volume of a cylinder. Now graphically, for functions of 2 variables, and this is what we're going to visualize, their graphs, because remember, if we go back and look at the graph here, it's kind of input, output. Now for a function of 2 variables, there's 2 inputs and 1 output, and therefore the graph is 3-dimensional. Now if you have 3 inputs, the graph is 4-dimensional. We can't visualize it anymore, but for the purposes of discussion, we're going to think about functions of 2 variables. And for functions of 2 variables, when you plot them, you end up with a surface. Now there's a little section here that you probably didn't do last year. I actually, when I teach that module, I do this section. It's just to get you thinking a little bit, and it can be a little bit useful. So we'll go through it. So in first year and chapter 2, we get away with simply saying differentiate and anti-differentiate. In the module you did in semester 3, in this one, in this particular section, you need to be a bit more precise. In particular, you want to understand what this symbol actually means. Okay, so a function, and this is just a real valued function, it's like the bending moment is a function of x, associates to an input x and output f of x. Input, output. So that's the real valued functions that you're familiar with from, say, semester 2 and chapter 2 in this. In first year, the inputs and outputs were both real numbers, but as maths gets more technical, we need to allow for more complicated objects for inputs and outputs. So for example, a matrix you can actually view as something that takes in a vector and spits out. An input is a vector and an output is a vector. So rather than just assuming that a function always maps numbers to numbers, a function can map objects to objects. So the character of a function is, you give it an input, it produces an output. The input and output do not have to simply be real numbers. They can be anything. Okay. Now, what I want us to do is to think about differentiation itself as a function. You give the input will be a function, and you do differentiation and you get another function. So the first function in is the input and its derivative is the output. So I'm just going to kind of look at that ahead. So for example, you can have a function which I'll just call, say, x cubed as an input, and then think of differentiation itself as a function. So the input is the f of x equal to x cubed, and then differentiate with respect to x, you get out the function x is sent to 3x squared. So this is input function, output function. So here we'll have a little look at this. So if we take the collection of all possible functions, now you have to be a bit careful, but we'll just assume that. So imagine that the inputs are functions. Now if you're unsure what a function is, real valued functions, you can actually think of them as just graphs. So the inputs are graphs. Say for example here 3x cubed. But if you think of all possible graphs, now I have to be very careful there. But the idea is that you've got an input function here. It's a function, and then you have an output function, which would be its derivative, which, as it happens, looks something like this. So this is maybe how you want to think about this. So you go from here. This function gets sent to this function, and you can think of it as a function itself, where the inputs and outputs are functions. And we are going to lose that language quite soon because it should be a bit confusing. So I have in my mind here a function that takes as an input a function and an output a function. So this symbol I'm calling this function. So it sends 2 to 0, 3x to 3, x squared to 2x, sine x to cos x, e to the x to itself, and log of x to 1 over x. What function is this? Well, it's the differentiate with respect to x function. Another notation for differentiate with respect to x is this d dx. So when you write d dx of, say, sine of x, you can kind of imagine this like f of x, function input, and the output when you differentiate sine of x is cos of x, for example. It's a perfectly good function, this thing, because it associates inputs, functions, to outputs, other functions. So this view, if you're a bit confused, that suits me fine, because you're putting in a function to a function, getting out a function. So I'm going to use the word operator or transform. It's just another word. So when the inputs are functions themselves, let's call this thing, rather than calling it a function, call it a transform or an operator to describe a function. Okay, now to be more specific, this thing is the differentiate with respect to x operator. Donated like this, we've done this already. Therefore, whenever you see this, it means differentiate with respect to x. So the operator differentiate with respect to x applied to this is equal to this via the chain rule. And compare this with, say, let's just write down a specific function, f of x equal to x squared. You want to compare this with f of, say, 7 is equal to 49. Input, output, same kind of setup. Similarly, you have to differentiate with respect to t operator, to differentiate with respect to or operator, and when you've got multiple variables, so for example here, for the maximum bending moment, I think this should be 8 actually, shouldn't it? Of a simply supported beam of, when the constant load is W and the beam is L, then the two, you can differentiate this with respect to W and L. These are the two variables. Now here's some other operators or transforms, and you can pause the video and try and think about what these things are. What sends 2 to 2x plus c? What sends 2 to 0? So this I also sends sine x to minus cos x plus c. It also sends x to the 4 to x to the 5 plus c. So have a think. What do you think this I is? Pause the video and have a think if you want. And what about this s thing? It sends 2 to 0, sine x to minus sine x, and the function x to the 4 to 12x squared. Now I'm calling them operators. The inputs are functions and the outputs are functions. So what we have on the next page, the I is the anti-differentiate operator. So now it's a little bit tricky because of the plus c, but you can tidy that up. The second operator is the differentiate with respect to x twice operator. Now I don't need to go much into this because I don't think, well, you need second derivatives for the previous section on Taylor series, but we don't need it here, so we don't have to go into it too much. We're not going to go back on this. We'll see if you pick the elective maths next semester, we'll be working with the Laplace transform, function in, function out, and then you're going to level 8, you'll see the Fourier transform. And if you want to say electrical, if you were to do electrical engineering, well, you're not now, but if you had done electrical engineering, you probably wouldn't call them the inputs to these transforms functions, you think of them as signals. So you get a signal in and you do some kind of a transform and you get a signal out. Okay. So now what we're going to do is partial derivatives. So we said, back here we said, oh, you could differentiate, say, with respect to t or with respect to r, and if there's multiple variables, so if a function depends on more than one variable, you want to be able to differentiate it separately with respect to these things. So this is what partial derivatives are. So essentially this is differentiation for functions of several variables. And really it's about us analyzing these things. So I wrote way back here that we could analyze this just looking at the formula, but you can analyze, functions of a single variable using calculus. You can find the maximum, the minimum. You can find out where they're increasing, where they're decreasing. These kind of things. Well, you use partial differentiation to do the similar thing for functions of several variables. This has two variables, b and h. Okay. Now, the way I'm basically just doing a full revision here, by the way. So the way, say if it's a function of two variables, you want to think of the graph as being a surface. So the way I visualize the graph of a function of two variables is like kind of the surface of the earth. And here's a question for you. You've got a mountain in front of you. Now, where am I? This, I think, is... I'm very embarrassed. I don't know which way is south here, but I think where I am, this is south. So, well, it doesn't make sense because this is flat down, but okay, just imagine that this is due south, and so actually I'm going to make it due north. It'll just make it a bit easier. So into the page is north, and if that's the case, y is west. Yeah, okay. So the question is, how does z, which is just the height, change as you change x? Now, what x means is, changing x means moving north. So basically traveling straight up the mountain. And z changing, z is just the height. And the question is, what is the rate of change in z as I keep y constant? So this is the big thing. If you travel exactly north here, we're not going to shimmy left and right. We're not going to go a little bit east and go a little bit west. We're going to go straight up the mountain. And if you do that, your east-west coordinate doesn't change. So y is like your east-west coordinate. That doesn't change. It's constant. So when you walk directly north, you don't move east and west at all. That's the idea of this picture. So what we're going to do is we're going to look at this from side on, and it might look something like this. So if y is a constant, so just that means walking straight up the mountain, you can take a kind of a cross section. That should be something you understand, and you get something like this. So this is traveling north, and this is the height. So this is kind of a side view, an idealized side view of walking up the mountain. Now we do have the height depends on x and y, your east-west coordinates and your north-south coordinates. But if we're going up here, we're fixing. There's no real y coordinates here. It's fixed. So what we're going to say, what the hell am I going to write here? I think what I'm going to write is that if z is a function of x and y is constant, you have that z is a function of x and b, but as b doesn't change, you can just think of this. I'm going to write this funny symbol, f of x. So you can think of this as z is equal to f of x. And traveling up the mountain, the rate of change is just pretty much the same as the slope. Rate of change of height, z, with respect to x is just the same as the slope. And now if we think about y as fixed, this is just a function of a single variable. We know how to find slope, it's just the derivative. So we just have to differentiate this thing. So the rate of change of f of x and y to x, the rate of f with respect to x at a particular point, so this would be like your x equal to a, when y is fixed at b, is the slope of the surface in the x direction. Okay, so let's see how we get on here. So what I'm going to do is I'm going to write the y equal to 2, but I'm not going to calculate 2 cubed and all that. It should hopefully make some kind of sense. So what we're going to do is we're going to kind of think about this. It's a function of two variables, but we're going to put y equal to 2 and think of it as a function of a single variable. So you have z is equal to x cubed plus x squared times 2 cubed minus twice 2 cubed. Now there's two things we want to write down, kind of some facts about differentiation that are very important. We have been doing it. We have been doing it in chapter 2. You know, when we're anti-differentiating the beam equations, we go term by term, fixing constants. That's anti-differentiation. It also works for differentiation. So if you're differentiating, so imagine this is a constant times some function of x, which I'm going to call f1 of x, plus a constant times some function of x. You're going to differentiate term by term, differentiate this and then this, but you can also fix constants. That's something we would have done in the revision in last week's lectures. So this would be fix the constant k1, then differentiate f1, f dash of 1, plus fix the constant k2, and then differentiate the other one. It's probably worth, so people get in a bit of bother here, because what happens is they get a bit confused between this and product rules and stuff. So I'm going to do that maybe just on the page overleaf. So just a little note here. So people get into trouble with, say y is some constant times f of x. And there's a bit of confusion between, like, the confusion is probably, so I'll call that y1. y2 then would be f of x plus a constant, and then we're going to have a third function y3, which would be two functions multiplied together. Okay, so the derivative of y3, it's two functions multiplied together, so you should use the product rule. Now, I appreciate I'm not actually specifying what these functions are, but I want to talk generally. You want to use some abstract maths. So it's the first thing times the derivative of the second thing, this is the product rule, plus the second thing times the derivative of the first thing. So that's the product rule. Okay, and then the second thing is, if you're differentiating this, I use the sum rule, which means you differentiate term by term. So the derivative of f of x is f dash of x, and the derivative of a constant is 0. Now, we get a bit of confusion then. I should have just written y2 here. We get a bit of confusion then when people differentiate y1. And the reason is, I'm not sure exactly why it is, but I just get people with different confusions. So some people say, why isn't the derivative of the constant 0? But it is. But there's a difference between a constant being added and a constant being multiplied. So if you say, oh, the constant is being multiplied, then you probably need to say to yourself, well, should I use the product rule? And let's see what happens when you use the product rule. It's the first thing by the derivative of the second thing, plus the second thing by the derivative of the first thing. And now it is true to say that the derivative of a constant is 0. And what's f of x times 0 is just 0. So you're just left with k times f dash of x plus 0. And rather than going through the product rule with these, you should just fix the constant and differentiate. And there's no contradiction between these two, because this is plus a constant, this is multiplied. Okay, so yeah, what we might see sometimes is if there's a constant on its own in this thing, they'll fix that constant, but that's added. It's only when it's multiplied. Anyway, so we're going to do that with this. And so if we differentiate this, now I'm going to write this. Okay, I better just use the right notation. So we don't write the normal dz dx here, because you could, but it gets a bit messy. So for various reasons we use this slightly different d, which isn't in any other alphabet, I think, as far as I know, except for maths. So we'll differentiate term by term. So the derivative of x cubed is 3x squared, plus, then fix the constant to cubed, it's constant, and then differentiate x squared, you get 2x. Fix the constant minus 2 cubed, and, well, what's the derivative? Okay, actually here it is, I've kind of contradicted myself. Well, the derivative of 2 is 0, but this whole thing is just a constant. So the derivative of a constant is 0. Okay, now the idea with partial differentiation is you don't specify what y is, you don't write in this 2, but when you're differentiating with respect to x, you treat it as if it is some fixed constant. So you differentiate it like this, except rather than with 2's, you'd have y's. So more generally, we fix y not equal to 2, but y some constant that we don't specify, and we differentiate, or we define the partial derivative of z with respect to x is the same thing as take z, put y equal to a constant, which we also call y, and then just differentiate it as normal. That's kind of what's going on. And similarly, you can do the partial derivative of z with respect to y. Now we'll do some examples.